In the garden at Woolsthorpe Manor, where sunlight filtered through leaves and dappled the ground in patterns that shifted with each breath of wind, where the orchard had stood for generations bearing fruit in its season, where young Isaac Newton had returned from Cambridge to escape the plague that ravaged England in 1665, in this garden that seemed untouched by history's larger movements, a moment occurred that would echo through centuries. An apple fell. Not the first apple ever to fall, not even the first apple that particular tree had surrendered to gravity's pull, but an apple that fell while someone was watching in a particular way, with a particular kind of attention, with the mind that would transform what everyone had always seen into what no one had truly understood. The story has been told so many times it has become legend, has been simplified and mythologized, has been reduced to the image of apple striking Newton's head and delivering instant revelation, as if understanding arrives complete and sudden like gifts from heaven rather than emerging slowly through years of patient thought, through careful observation, through mathematical labor that transforms initial wondering into demonstrable law. But the legend carries truth even while distorting details. Something did happen in that garden, some recognition did occur. Whether the apple actually fell, or whether Newton simply contemplated falling apples while sitting in the orchard's shade, whether the insight arrived in a flash or developed gradually over months of reflection, these questions matter less than the recognition that changed everything. What Newton understood was this: the force that pulls the apple downward might be the same force that holds the moon in orbit around Earth, that keeps planets circling the sun, that prevents the cosmos from flying apart into chaos. The falling apple and the orbiting moon seemed like completely different phenomena, one terrestrial and ordinary, something that happens countless times every day, the other celestial and extraordinary, the eternal dance of heavenly bodies that had inspired awe and worship since humans first looked upward. But Newton dared to imagine they were the same, that the distinction between earthly and heavenly physics was false, that the universe was unified, that one law might govern both the orchard and the cosmos. The daring of this insight is difficult to appreciate from our current perspective, from the side of the revolution that Newton accomplished. We now take for granted that physics is universal, that the laws operating on Earth apply equally in the heavens, that there is no fundamental distinction between terrestrial and celestial phenomena. But before Newton, this unity was not obvious. Aristotelian physics had taught for nearly 2 millennia that the heavens and earth were fundamentally different realms governed by different principles. Earthly matter was composed of 4 elements and moved naturally toward or away from Earth's center. Celestial matter was quintessence, perfect and eternal, moving in perfect circles because circular motion was natural to it. The heavens were realm of perfection, unchanging and divine. Earth was realm of imperfection, changing and mortal. Newton's genius was recognizing that this distinction was unnecessary, that a single principle could explain both falling apples and orbiting moons, that what made the apple descend and what kept the moon from flying away into space might be identical universal gravitation, the force by which every mass attracts every other mass, the invisible architecture that structures the cosmos and prevents it from dissolving into unrelated particles drifting through void. The recognition required more than casual observation, required mathematics that could calculate gravitational force, that could demonstrate the moon's orbit was indeed a form of falling, that the moon was perpetually falling toward Earth but also perpetually missing it because of its tangential velocity, that orbit is balance between falling and fleeing, between gravity's pull and inertia's persistence. But Newton in 1665 was not yet ready to develop this insight fully, did not yet possess the mathematical tools necessary to demonstrate what he suspected, did not yet have calculus that could handle motion and change, that could calculate instantaneous velocities and accelerating forces, that could translate intuition about gravity into rigorous proof. The apple fell in 1665, but the Principia would not be published until 1687, 22 years of thought and calculation and development separating initial insight from complete demonstration. The gap between wondering and knowing, between suspecting and proving, between glimpsing truth and expressing it mathematically, this gap consumed decades of Newton's life, required developing entirely new mathematics, required patient observation of planetary positions, required courage to challenge received wisdom about heavenly physics. The apple became symbol because it captured something essential about how understanding advances not through abstract speculation alone, not through pure mathematics divorced from observation, but through attention to ordinary phenomena, through refusing to accept that familiar things require no explanation, through insisting that what everyone knows must still be understood, must be subjected to inquiry, must be made to reveal the principles underlying what seems merely obvious. The apple falls. Everyone knows this. No one questioned why until Newton made the familiar strange, made the obvious mysterious, made the everyday phenomenon into doorway through which to enter cosmic understanding. We sit in that garden now, centuries later, knowing what Newton's question led to knowing about gravity and planetary motion and the mathematics that captures them, knowing that his insight was correct, that the moon does fall like the apple falls, that universal gravitation does structure the cosmos, that the laws Newton discovered from watching apples do govern the heavens. But try to return to the moment before knowing, to the garden before the question, to the world where apples simply fell because falling was their nature, where no explanation was needed because things were as they were and that sufficed. Try to feel the shift when someone asks why, when familiar becomes questionable, when the obvious demands explanation. This is what Newton gave us, not just the specific laws of motion and gravitation, not just the mathematical framework that would dominate physics for 2 centuries, but the example of attention, the demonstration that patient observation combined with mathematical rigor can unlock nature's secrets, that the universe will yield its principles to anyone who asks carefully enough, who watches closely enough, who refuses to accept mystery as final answer. The apple fell through certainty into question, through acceptance into inquiry, through the familiar into the strange, opening the path that Newton would follow for decades, that would lead to the Principia, that would rewrite physics and astronomy and humanity's understanding of the cosmos. But even as we celebrate the insight, as we honor the genius that saw unity where others saw division, we must acknowledge what the falling apple inaugurated: the mechanization of nature, the reduction of cosmos to machine, the transformation of the universe from living creation into clockwork mechanism operating according to fixed laws, beautiful and elegant and comprehensible, but also somehow diminished, made less than it had been when mystery was acceptable, when divine action was immediate. When nature's operations required no explanation beyond God's will. Newton himself saw no conflict, believed that discovering natural law was discovering divine wisdom, that understanding mechanism was understanding the mind of God. But later generations would read the mechanical universe differently, would find in Newton's laws the beginning of disenchantment, the first step toward cosmos that needs no God, that runs by itself according to principles that require no supernatural intervention. The apple falls through certainty, opening questions that Newton would spend his life answering, questions that science would pursue for centuries, questions that remain even now after relativity and quantum mechanics have revised Newton's laws, questions about why there is order rather than chaos, why mathematics describes nature, why the universe submits to comprehension, why an apple falling in an English garden could become doorway to cosmic understanding. Symbol of how genius transforms the familiar into revelation, the everyday into entrance to the extraordinary, the simple fall into complex law, the apple into cosmos, the garden into universe, the watching into understanding that changed everything, that made Newton's name synonymous with genius, that gave us the laws of motion and gravitation, that showed the heavens and earth obey the same principles, that unified physics, that made science possible as systematic investigation of natural law. That began with Apple falling through certainty into question, through acceptance into inquiry, through the garden where Newton sat watching, wondering, beginning the journey that would lead to the Principia, to the laws that shaped our understanding, to the genius that transformed human knowledge of the cosmos, all beginning here in the garden, with the apple falling, with Newton watching, with the question that would not let him rest until he found the answer, until he developed the mathematics, until he wrote the laws. Until the apple's fall was explained through universal gravitation, through the force that structures cosmos, through the insight that began in a garden where an apple fell and genius watched and nothing would ever be quite the same. The apple falling through certainty, opening the future, beginning the revolution, starting the journey that this chapter honors, that this night explores, that brings us to Newton's garden where we sit now, watching the apple fall, feeling the question form, understanding beginning to dawn. The laws waiting to be discovered, the cosmos waiting to be explained, the apple falling through certainty into wonder, into inquiry, into the mind that would not rest, into the genius that would transform everything, the apple falling, Newton watching, history shifting, certainty cracking, wonder emerging, the journey beginning here, now in the garden, the apple falling through certainty. In the shuttered room at Trinity College, where Newton had excluded the world to study what the world was made of, where sunlight entered only through a carefully controlled aperture, where darkness was necessary for understanding illumination, in this chamber of deliberate shadow, light revealed its secrets. Not all at once, not through single dramatic experiment, but slowly, through patient observation, through precise measurement, through the discipline of asking the same question repeatedly until nature could no longer remain silent, until light itself confessed that it was not what it appeared to be, that the white brilliance we trust without question contains within itself an entire spectrum, a rainbow hidden in plain sight, colors that were always there but invisible until prism revealed them. The year was 1666, the plague year that had sent Newton from Cambridge to Woolsthorpe and back again, the year of apples falling and light dividing, the annus mirabilis when Newton's genius bloomed in isolation, when forced retreat from academic life paradoxically became most productive period of his youth, when being alone with questions proved more fruitful than being surrounded by scholars, when the shuttered chamber taught more than the libraries and lecture halls could have taught. Newton had obtained a prism, a triangular piece of glass that street vendors sold as curiosity, as toy that produced pretty colors when sunlight passed through it. But where others saw entertainment, Newton saw mystery demanding investigation. Why did glass bend light? Why did bent light separate into colors? Were the colors created by the prism or revealed by it? Was white light simple or composite? How many colors were there? Could they be further divided, or were they fundamental? The questions multiplied faster than answers could be found, each observation raising new puzzles, each experiment suggesting further experiments, the simple prism becoming instrument for interrogating light itself, for forcing illumination to explain itself, for transforming familiar phenomenon into scientific investigation. Newton worked methodically, varying conditions, measuring angles, recording results with precision that would characterize all his experimental work, refusing to accept appearance as sufficient, insisting that phenomena must be understood, must be subjected to mathematical analysis, must yield principles that could be expressed precisely rather than remaining merely qualitative observations that satisfied curiosity without producing knowledge. He began by admitting single beam of sunlight through a small hole in the window shutter, allowing only narrow ray to enter the darkened chamber, creating the isolation necessary for careful study, for seeing clearly what diffuse light obscures. The beam passed through the prism and struck the opposite wall, not as white circle but as elongated spectrum, as rainbow of colors arranged in definite order: red, orange, yellow, green, blue, indigo, violet, each color occupying its position, each shade blending into the next, the whole forming continuous band that seemed to contain infinitely many hues, even though Newton would identify 7 primary colors, influenced perhaps by desire to find numerical harmony. To make optics match the 7 notes of musical scale, to find in light the same mathematical patterns that governed sound. But the crucial experiment came next, the demonstration that would establish Newton's understanding of light's nature, that would prove white light is composite rather than simple, that would show prism reveals rather than creates colors. Newton placed second prism in the path of one of the colored beams, isolated red light from the spectrum, and passed it through another prism, wondering whether this second refraction would produce further division, whether red could be split into additional colors just as white had been divided into spectrum. It could not. The red light remained red, was refracted by second prism but was not further divided, emerged still red, demonstrating that individual colors are fundamental, that spectrum's components cannot be further decomposed, that white is mixture while red and blue and yellow are pure. The discovery transformed understanding of color, showed that color is property of light itself rather than being modification of white light, that different colors bend differently through glass, that prism separates white into spectrum because white contains all colors and because each color refracts at slightly different angle, that rainbow is not created by prism but is revealed by it. Was always present in white light but became visible only when prism separated components that normally travel together, that strike eye simultaneously and create sensation of white, of colorless illumination that conceals the spectrum within it. Newton's optics went further, investigated how colors combine, demonstrated that spectrum could be recombined into white by passing it through inverted prism, showed that color addition and subtraction follow definite rules, that mixing lights produces different results than mixing pigments, that there are primary colors from which others can be composed, that vision itself involves selective sensitivity to different wavelengths. That seeing color requires both light of appropriate frequency and eye capable of detecting it. The work was meticulous, was grounded in careful experiment and mathematical analysis, was presented with rigor that made his conclusions difficult to dispute, even though dispute came nonetheless, even though his theory of colors was controversial, even though some philosophers rejected his results because they contradicted Aristotelian optics, or because they seemed to reduce color to mechanism, or because they challenged cherished beliefs about light's nature. But beneath the experimental findings, beneath the specific discoveries about refraction and spectrum and color, lay deeper mystery that Newton recognized but could not fully resolve. What is light? Is it stream of particles flowing from luminous objects, or is it wave propagating through medium, or is it something else entirely that exhibits both particle-like and wave-like properties depending on how it is observed? Newton favored corpuscular theory, believed light consisted of tiny particles emitted by light sources, traveling in straight lines, reflecting from surfaces, refracting through transparent media. The theory explained much, explained shadows with sharp edges, explained reflections' regularity, explained refraction through impact of particles entering different media. But it struggled with other phenomena, with interference patterns that seemed to require waves, with diffraction that particles could not easily account for, with behaviors that suggested light was more complex than either particles or waves alone could explain. The mystery deepened across centuries as evidence accumulated for both particle and wave nature, as experiments demonstrated that light behaves sometimes like particles, sometimes like waves, that it resists being captured by single description, that nature at fundamental level is stranger than classical physics imagined, that light carries within itself paradox that quantum mechanics would eventually embrace though never fully resolve. That the familiar phenomenon we call light remains in essential respects mysterious, that even after centuries of investigation we cannot quite say what light is, can only describe how it behaves under various conditions, can measure and calculate and predict without being able to explain in simple terms what light fundamentally is, what kind of thing can be both particle and wave, how illumination that seems so familiar can be so strange when examined carefully. Newton sat in the darkened chamber, watching colored beams paint the wall, measuring angles with geometric precision, developing theory that would dominate optics for generations, revolutionizing understanding of light and color and vision. But he also confronted mystery that his experiments revealed but could not dispel, recognized that understanding raises questions even while answering others, that light yields some secrets while preserving others, that the spectrum is real and the measurements are precise and the mathematics works perfectly, but that beneath successful description lies persistent uncertainty about light's fundamental nature, about what kind of entity can behave as Newton's experiments demonstrated, about whether particles or waves or something beyond both categories is required to explain illumination's full range of behaviors. The chamber where light became particle and wave, or perhaps where light revealed itself to be both or neither, or something that transcends the distinction, this chamber stands now as symbol of how understanding advances, how experimental investigation combined with mathematical analysis can penetrate nature's operations, can discover laws governing familiar phenomena, can transform light from obvious reality into scientific subject, from accepted background of existence into object of rigorous study. Newton showed that careful observation rewards those patient enough to sit in darkness, to control conditions precisely, to measure accurately, to refuse easy answers, to keep asking until nature responds, to accept that responses may raise new questions, that understanding is never complete, that even light most familiar of phenomena remains mysterious after investigation, remains stranger for being studied than it was when merely accepted, remains in its essence elusive even while its behaviors become predictable, mathematically describable, subject to laws that Newton helped discover but that did not exhaust light's mystery, did not reduce illumination to mechanism completely, left something unexplained, left questions for later physics, left the paradox of particle and wave for quantum mechanics to inherit without fully resolving. Left us with light that works precisely according to equations, but that remains in its fundamental nature mysterious, beautiful, strange. The light that Newton studied in chambers where darkness was necessary for seeing, where exclusion of world was required for understanding world, where shuttered rooms became laboratories, where prisms became instruments of investigation, where light became subject rather than merely condition, where illumination revealed itself to be more complex than anyone had imagined, where the spectrum emerged from white, where colors showed themselves to be fundamental, where Newton's genius transformed optics, where the chamber where light became particle and wave stands as monument to patient investigation, to experimental rigor, to mathematical physics applied to familiar phenomena, to the understanding that advances slowly through careful work, through precise measurement, through refusing to accept appearance as sufficient, through sitting in darkness to understand light, through the discipline of shutting out the world to see the world clearly, through the chamber where Newton sat alone with prism and beam, discovering that light is spectrum, that white is composite, that colors are fundamental, that illumination is more strange than familiar, more complex than simple, more mysterious than obvious, the chamber where light revealed itself while preserving its mystery, where Newton understood and wondered both, where genius discovered laws while recognizing limits of discovery, where the familiar became strange and the strange became subject to mathematics, where light became particle and wave, where Newton gave us optics while light gave us mystery, where the chamber stands in memory as place where darkness enabled seeing, where isolation enabled understanding, where shuttered room became laboratory of illumination, where light revealed what words can barely capture, what equations describe without explaining, what remains even now after centuries of investigation somehow mysterious, somehow strange, somehow more wonderful for being studied, more sacred for being understood, the light that Newton investigated that divided into spectrum, that became particle and wave, that revealed itself in the chamber, in the darkness, in the beam passing through prism, in the rainbow appearing on the wall, in the measurements that Newton recorded, in the theory that he developed, in the understanding that emerged, in the mystery that persisted, in the chamber where light became particle and wave, where Newton's genius met light's mystery, where optics was born, where illumination was studied, where the spectrum was revealed, where the chamber stands, where light became particle and wave, where understanding advanced, where mystery deepened, where Newton sat, where we remember, where light becomes particle and wave, eternal in the chamber where Newton discovered spectrum. Before Newton, mathematics spoke eloquently about being but struggled with becoming, could measure static quantities with precision but foundered when confronting change, could calculate areas of fixed shapes and distances between stationary points but could not quite grasp motion, could not capture in symbols and equations the continuous flow of time, the smooth acceleration of falling bodies, the varying speed of planets, the instantaneous rate at which things transform. Geometry described space perfectly, could prove theorems about circles and triangles that would remain true forever, but time eluded it, change resisted it, becoming remained outside mathematics' reach, or at least outside the mathematics that existed before Newton created the new language necessary for speaking about motion, for capturing change itself in symbols, for making the flowing world subject to calculation. The problem that demanded solution was planetary motion. Kepler had discovered empirical laws describing how planets orbit, how their speeds vary as they sweep around elliptical paths, how orbital periods relate to distances, but these laws were observations rather than explanations, were descriptions of what happens rather than demonstrations of why it happens, were patterns noticed but not derived from deeper principles. To understand why planets move as Kepler described, to demonstrate that their motions follow necessarily from gravitational attraction and laws governing all motion, Newton needed mathematics that could handle continuously varying quantities, that could calculate velocities that change from instant to instant, that could determine the curve of a planet's path from knowledge of forces acting on it, that could translate from acceleration to velocity to position and back again. Revealing how these quantities relate, how they determine one another, how understanding one gives access to the others. The mathematics Newton created to solve this problem was calculus, though he called it method of fluxions, thinking of quantities as flowing, as being in continuous flux, as changing smoothly rather than jumping discontinuously, as being better captured by rates of change than by static values. The fundamental insight was focusing on instantaneous rates, not average velocity over an interval, but velocity at a single moment. Not total change across time, but rate of change at an instant, the slope of a curve at a point, the acceleration at a moment, quantities that seemed paradoxical because they involved ratios of infinitesimally small changes, dividing zero by zero in a sense, working with quantities that approached zero without being zero. That vanished when you tried to grasp them directly, but that could be captured through limiting process, through considering what happens as intervals become smaller and smaller, approaching zero, while revealing in their approach the instantaneous rate that calculus names the derivative. Newton's notation was geometric and intuitive, thinking of flowing quantities and their rates of flow, using dots above letters to indicate derivatives, developing rules for calculating rates of change of sums and products and quotients and powers, showing that derivatives could be found systematically for all functions built from basic operations, that the process could be reversed through integration to reconstruct original quantity from knowledge of its rate of change. That derivative and integral were inverse operations, two sides of calculus that together gave complete language for describing motion, for translating between position and velocity and acceleration, for solving problems that had resisted all previous mathematical approaches. But even as he developed these powerful tools, even as he used calculus to solve problem after problem, calculating planetary orbits, determining curves of optimal resistance, finding tangent lines and areas under curves, Newton recognized that his methods raised philosophical questions about infinitesimals, about whether these vanishing quantities were real or merely convenient fictions, about how ratios of zeros could yield finite answers, about whether his procedures were rigorous or merely worked by lucky accident. He could not fully answer these questions, did not have foundations that would satisfy philosophical scrutiny, operated with intuitions that were mathematically fruitful but logically questionable, using infinitesimals that seemed to be zero when that was convenient and non-zero when that was necessary, achieving correct results through methods that seemed to involve sleight of hand, treating quantities as simultaneously negligible and significant depending on context. The paradox troubled him less than it troubled later mathematicians who would spend 2 centuries cleaning up calculus's foundations, who would replace Newton's infinitesimals with rigorous theory of limits, who would make calculus respectable by eliminating intuitive but questionable concepts, by replacing Newton's flowing quantities with static functions and precise definitions of continuity and differentiability, by showing that calculus could be rebuilt on firm logical ground without infinitesimals, that limits captured what Newton had grasped intuitively, that his methods worked not by accident but by approximating precisely defined limiting processes that could be made rigorous even though Newton himself had not made them so. But for Newton, calculus was tool for understanding nature rather than mathematical structure requiring rigorous foundation, was means to solving physical problems rather than object of study in its own right, was language for expressing natural law rather than abstract system requiring internal consistency above all. He developed calculus because physics demanded it, because understanding planetary motion required mathematics that could handle continuous change, because natural philosophy could not advance without tools for calculating velocities and accelerations and orbital paths, because the universe itself is characterized by becoming, by motion, by continuous transformation that mathematics must capture if it is to describe nature adequately. If it is to make physics into science, rather than remaining merely qualitative description. The remarkable fact that mathematics invented to solve specific physical problems turned out to have far wider application, that calculus worked not just for planetary motion but for all continuous change, that the same methods Newton developed for gravitational problems could handle heat flow and population growth and economic change and fluid dynamics and electromagnetic fields and quantum wave functions, that calculus became the language of all mathematical science. The indispensable tool for describing any process involving continuous change, this universality suggests something profound about relationship between mathematics and nature, about why the universe submits to mathematical description, about whether mathematics is discovered or invented, about whether the harmony between mathematical structures and physical processes is mere coincidence or reveals something deep about reality's structure. Newton believed mathematics reflected divine thought, that the mathematical patterns governing nature were not arbitrary human constructions but were actual structures of creation, were the language God used in designing universe, were accessible to human reason precisely because human reason participated in divine reason, because we were made in image of God, and therefore our rational faculties could grasp the rational principles by which God created and governs cosmos. The calculus that captured becoming was for Newton not just useful tool, but was revelation of how God structured continuous change, how divine wisdom made motion lawful, how the Creator ensured that the flux would be comprehensible, that becoming would submit to mathematics, that continuous transformation would yield to analysis, would reveal its secrets to anyone patient enough to develop the mathematics necessary for grasping it. But whether Newton's theological interpretation is accepted or not, whether we believe mathematics reflects divine thought or is merely powerful human construction, the achievement remains Newton gave us language for describing change, mathematics for capturing motion, methods for calculating what previously resisted calculation, tools that would make mathematical physics possible, that would allow quantitative science to advance into all domains characterized by continuous variation. That would show becoming is no less mathematical than being, that flux is subject to law, that motion can be captured in equations, that change itself yields to analysis, that the calculus works, that derivatives and integrals do what they promise, that the mathematics Newton created for understanding planetary orbits applies universally to everything that changes, to all processes characterized by continuous variation, to all of nature that flows, that transforms. That becomes rather than simply being, all of this captured in calculus, in the method of fluxions, in the mathematics that Newton created to understand motion, but that transcended its origin, that became universal language, that gave us the tools for mathematical science, that made physics possible as quantitative discipline, that showed becoming is comprehensible, that change submits to law, that motion can be mathematized, that the flowing world yields to symbols. That calculus captures what seemed uncapturable, that mathematics grasps what seemed elusive, that becoming is no less lawful than being, no less mathematical than the static geometry that preceded calculus, no less subject to precise analysis than the fixed quantities that earlier mathematics handled perfectly. The calculus showing that mathematics can grow, can develop new languages for new problems, can create tools that nature accepts, that physical world responds to. That work because mathematics and nature correspond, because the universe is mathematical in its becoming as well as its being, in its processes as well as its structures, in its changes as well as its constancies, all of this revealed through calculus, through the mathematics Newton created when he needed tools that didn't exist, when physics demanded new mathematics, when understanding motion required inventing the language for describing it. When planetary orbits could not be calculated with geometry alone, when becoming demanded its own mathematics, when Newton gave us calculus, when he captured change in symbols, when he made motion mathematical, when he created the fluxions, when he developed the methods, when he solved the problems, when he gave us the calculus that captured becoming, that made physics possible, that became universal language, that revealed becoming is mathematical, that showed change submits to law. That demonstrated motion can be captured, that proved the flowing world yields to symbols, that gave us the mathematics of becoming, the calculus that captures change, that makes motion comprehensible, that translates becoming into mathematics, that Newton created, that we inherit, that science uses, that works because becoming is mathematical, because change is lawful, because motion submits to analysis, because the universe accepts the mathematics that Newton created when he gave us calculus. When he captured becoming, when he made change mathematical, when he translated motion into symbols, when he created the language for describing what flows, what transforms, what becomes rather than simply being, giving us the calculus that captures becoming. In 17 months between 1685 and 1687, withdrawn from society, consumed by vision that demanded complete focus, Newton wrote Philosophiae Naturalis Principia Mathematica, the mathematical principles of natural philosophy, 3 books that would stand as supreme achievement of human reason, as the work that demonstrated what genius combined with mathematics could accomplish when applied to understanding nature. The Principia was not merely collection of observations or compilation of previous knowledge. It was systematic reconstruction of physics from first principles, was demonstration that the universe operates according to laws that reason can discover and mathematics can express, was proof that the heavens and earth obey same principles, was the book that unified celestial and terrestrial physics into single framework, that showed planetary motion and falling apples follow from same fundamental law, that revealed cosmos as machine operating according to principles humans could comprehend. The 17 months of writing were period of almost inhuman concentration. Newton slept little, ate irregularly, forgot meals that servants brought, existed in state of sustained intellectual intensity that few humans ever achieve, that came at cost we can only guess, that required him to withdraw from normal life completely, to exist almost entirely within the world of thought, to live in the problems he was solving, the proofs he was constructing, the laws he was formulating. His colleagues reported that he seemed barely present even when physically visible, that his mind was elsewhere, that he moved through the world like sleepwalker, aware only of the mathematics unfolding in his thoughts, the demonstrations taking shape, the system emerging that would rewrite humanity's understanding of the cosmos. The work began with Edmund Halley's visit in 1684, with the question about planetary orbits. If gravity diminished with square of distance, what shape would planetary paths take? Newton answered immediately, ellipses. Halley asked for proof. Newton said he had calculated it years earlier but had misplaced the papers. Would he work it out again? This casual request ignited the fire that produced the Principia, that transformed scattered insights Newton had developed over decades into systematic presentation, that moved from private understanding to public demonstration, that took what Newton knew and made it knowledge that could be shared, could be checked, could be built upon by others, could become foundation for scientific tradition rather than remaining merely individual achievement. The structure Newton created was mathematical and axiomatic, beginning with definitions: mass, quantity of motion, impressed force, centripetal force, carefully specifying terms whose meanings would be precise, would support rigorous demonstration, would allow mathematics to take over from qualitative description. Then came the three laws of motion that still bear Newton's name, that still form foundation of classical mechanics even though physics has moved beyond them, that capture in deceptively simple statements profound insights about how motion works, how forces affect it, how actions and reactions balance, how inertia persists until force changes it. First law: every body perseveres in its state of rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by forces impressed. The law seems almost trivial, stating what appears obvious: things keep doing what they're doing unless something makes them change. But the law was revolutionary, contradicting Aristotelian physics that claimed motion required constant force, that bodies naturally slowed and stopped unless continuously pushed, that rest was natural state toward which things returned. Newton declared that motion and rest are equivalent states, that uniform velocity persists just as rest does, that change requires force but continuation does not, that inertia is real property of matter rather than being mere tendency toward rest. Second law: the change of motion is proportional to the motive force impressed and takes place in the direction of the straight line in which that force is impressed. More familiarly now expressed as F equals ma, force equals mass times acceleration, the equation capturing how forces produce accelerations, how larger forces produce greater changes, how more massive bodies resist acceleration more than less massive bodies, how force and acceleration point in same direction, how all of this can be calculated precisely if force and mass are known, how motion becomes mathematical. How mechanics becomes quantitative science capable of precise predictions rather than remaining qualitative description that can only say roughly how things move. Third law: to every action there is always an opposed and equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. The law establishes that forces come in pairs, that when A pushes B, B pushes A equally, that interactions are reciprocal, that universe conserves momentum, that action and reaction are simultaneous and equal, that isolated systems maintain their total motion even as internal parts redistribute it, that the laws governing motion are universal, applying to all bodies whether celestial or terrestrial, whether massive planets or tiny particles, whether visible matter or invisible forces acting across space. From these three laws, from the definitions that preceded them, from the mathematical methods that Newton deployed with unprecedented rigor, the Principia derived everything explained: how projectiles move in parabolic paths, how pendulums swing, how bodies orbit under central forces, how gravitational attraction produces Kepler's empirical laws of planetary motion, how moons influence tides, how Earth's rotation causes equatorial bulge, how comets travel in elongated ellipses that bring them near the sun periodically before flinging them back to system's outer reaches. Problem after problem yielded to Newton's methods. Phenomenon after phenomenon proved to follow from fundamental principles, the cosmos revealing itself to be comprehensible, to be governed by laws, to be machine elegant, beautiful, mathematical machine, operating according to principles that Newton's genius had discovered. But the Principia could not explain everything, could not answer all questions that its success raised. Most troublingly, it could not explain what gravity is, how force acts across empty space, how sun reaches out to distant planets without any medium carrying the influence, how action at a distance occurs when all familiar forces require contact, require something pushing directly against something else, require mechanical connection rather than mysterious attraction operating through void. Newton proved that gravity exists, calculated precisely how it acts, predicted its effects with accuracy that left no doubt, but could not say what it is, how it works, why masses attract, what carries the force across emptiness separating planets from sun. "I frame no hypotheses," he wrote, acknowledging that his physics described how things move without explaining why motion occurs, calculated gravitational effects without explaining gravitational cause, made action at a distance into law without making it comprehensible, leaving gravity as a cult quality, as mysterious force whose existence mathematics demonstrated but whose nature philosophy could not grasp. Critics seized on this, argued that Newton had not really explained anything, had merely described, had given mathematical account of phenomena without providing mechanical explanation, had failed to show how gravity works and therefore had not achieved genuine understanding, but had only traded one mystery for another. Newton responded that calculation sufficed, that being able to predict precisely was achievement enough, that demanding mechanical explanation of gravity was asking for what might not exist, that nature might operate through action at a distance without any mechanism, that mathematics could describe reality even when philosophy could not comprehend it. That the Principia's success in predicting planetary positions and explaining tidal variations and accounting for comets proved its truth even if gravity's nature remained mysterious. The response was unsatisfying to those who wanted understanding to be complete, who wanted physics to provide mechanisms, not just mathematics, who wanted to know how as well as what, who wanted nature to make sense, not just submit to calculation. But the Principia succeeded nonetheless, transformed physics despite leaving gravity unexplained, rewrote astronomy despite not knowing what attraction is, made Newton's name immortal despite the incompleteness, became the foundation on which classical physics would build for 2 centuries, demonstrated what mathematical science could achieve, showed that nature yields to systematic investigation, that laws can be discovered and tested and applied, that the universe is comprehensible at least in its operations if not in its ultimate nature, that the heavens can be rewritten, that the cosmos can be explained, that the Principia accomplished what seemed impossible, unified celestial and terrestrial physics, derived planetary motion from fundamental laws, showed the universe is machine governed by mathematics, made physics into science, gave us the foundation, rewrote the heavens, changed everything. The 17 months producing the work that would shape 3 centuries of thought, that would make Newton supreme genius, that would demonstrate what human reason could accomplish, that would give us the laws that would explain the cosmos, that would rewrite the heavens through the Principia that stands as monument to genius, to mathematical physics, to systematic understanding, to the work of 17 months that Newton gave us, that rewrote the heavens, that changed how we understand the universe. That made physics possible, that gave us the laws that shaped our understanding for centuries, that demonstrated what genius could achieve, that showed mathematics describes nature, that proved the universe is comprehensible, that gave us the Principia that rewrote the heavens. While the public Newton revolutionized physics and astronomy, while he wrote the Principia and served as president of the Royal Society and became symbol of Enlightenment rationality, another Newton labored in secret in locked chambers where furnaces burned and substances transformed, where ancient texts were studied and experiments conducted, where the search was not for mathematical laws but for something older, something the modern world was forgetting, something that alchemy promised. The transmutation of base metals into gold, the discovery of the philosopher's stone, the uncovering of nature's deepest mysteries through chemical operations rather than through mathematical abstractions. The extent of Newton's alchemical work remained hidden for centuries, known only through manuscripts that were not published during his lifetime, that would not become available to scholars until the 20th century, that would reveal Newton spent more time on alchemy than on the physics that made him famous, wrote over 1,000,000 words on alchemical subjects, conducted countless experiments seeking transmutation, believed until his death that nature held secrets beyond what the Principia captured. That ancient wisdom contained truths that modern philosophy had lost. The contradiction troubles those who want Newton to be pure rationalist, who want him to embody scientific method completely, who want the founder of classical mechanics to have rejected occult qualities and hidden powers, to have recognized that alchemy was superstition being superseded by chemistry, that transmutation was impossible fantasy being replaced by genuine understanding of matter's true nature. But Newton saw no contradiction, pursued physics and alchemy simultaneously, believed both revealed nature's truths, thought mechanism and transmutation were compatible rather than contradictory, saw the universe as richer than pure mechanism allowed, as containing active principles and organizing powers that mathematics could describe but could not explain, that pointed toward something beyond mechanism even though mechanism was real and powerful and illuminating. The alchemical manuscripts show Newton studying ancient texts, copying recipes, conducting experiments with mercury and lead and sulfur, seeking the processes that would produce transmutation, that would reveal nature's secrets, that would give access to powers that the ancients possessed but that modernity had forgotten. He believed Moses and Solomon and Hermes Trismegistus had known truths about nature that Newton hoped to recover, that ancient wisdom was real, that the Prisca Sapientia, the pristine knowledge possessed by earliest humans, had been lost but could be found again through careful study of texts that preserved it in coded form, through experiments that would unlock what the codes concealed. The work was painstaking, heating substances for months, observing color changes, recording when materials fused or separated or transformed, looking for the signs that indicated progress toward the philosopher's stone, toward the substance that would enable transmutation, that would reveal nature's ultimate secrets, that would give power over matter that mechanical philosophy said was impossible, but that alchemy insisted was real, was achievable. Was the goal that dedicated investigators could reach if they persevered, if they understood the codes, if they performed the operations correctly. Newton never found the philosopher's stone, never achieved transmutation, never produced gold from lead, no matter how many experiments he conducted, how many texts he studied, how many years he devoted to the quest. The alchemy failed as science, did not discover what it sought, did not reveal secrets it promised, did not give Newton the powers he hoped for. But perhaps the alchemy succeeded in other ways in keeping Newton aware that mechanism had limits, that reducing nature to matter in motion left out too much, that the universe might contain organizing principles that physics could not capture, that action at a distance might involve something like alchemical active principles rather than being pure mechanism. The calculus of gravity, the force acting across empty space without mechanical connection, troubled Newton precisely because it seemed occult, seemed to involve hidden powers rather than mechanical interaction, seemed closer to alchemy than to proper mechanical philosophy. Perhaps his willingness to accept gravitational attraction, despite not understanding its mechanism, was supported by his alchemical belief that nature contains powers beyond what mechanism explains, that the universe is not merely machine, but is something richer, more mysterious, more alive than the mechanical philosophy allowed. The secret chambers where Newton practiced alchemy were not failures of rationality, but were recognitions that rationality has limits, that mechanism cannot explain everything, that the universe resists complete reduction to mathematics and matter in motion, that there are mysteries beyond what the Principia captures, questions that physics cannot answer, dimensions of nature that remain elusive even after mechanical explanation succeeds in its proper domain. Newton was both mechanist and alchemist, both physicist and mystic, both the founder of classical mechanics and the seeker of transmutation, both the man who gave us universal gravitation and the man who believed in the philosopher's stone. Later generations wanted to separate these Newtons, wanted to celebrate the physicist while ignoring the alchemist, wanted to preserve what fit the image of Enlightenment rationality while dismissing what troubled it, wanted Newton to be pure scientist rather than the complex, contradictory figure he actually was. But the real Newton cannot be simplified, will not fit our categories, remains strange where we want clarity, mystical where we want rationality, alchemical where we want scientific, refusing to be made into icon of reason alone, insisting through his manuscripts that he was more, was stranger, was someone who believed in both gravity and gold, both mathematics and transmutation, both the mechanical universe and the living cosmos. Both the physics that worked and the alchemy that failed, but that revealed the man's complexity, the genius's depth, the recognition that the universe is more than mechanism, even though mechanism is marvelous, that nature holds mysteries beyond what physics captures, even though physics captures much. The alchemy danced in secret chambers while the world praised physics, while history celebrated the Principia, while Newton became symbol of rationality even though Newton himself was so much more, so much stranger, pursued so much that does not fit the legend, that reveals genius cannot be reduced to its successes, cannot be separated from its mysteries, cannot be made simple when it was profoundly complex, the alchemy showing us the Newton who was both and neither. Who was rational and mystical, who was scientist and seeker, who gave us laws while seeking stones, who was all of this, who danced in secret chambers with transmutation, with ancient wisdom, with mysteries that the modern world dismisses but that Newton honored, pursued, believed in even while revolutionizing physics, even while giving us the mechanical universe, even while becoming symbol of Enlightenment reason, the secret chambers holding the other Newton, the alchemist, the mystic. The seeker of transformation, both physical and spiritual, the alchemy dancing in chambers that were locked, that were private, that were secret, that history discovered centuries later, that revealed the complexity, that showed genius is stranger than legend, more mysterious than fame, more contradictory than celebration, the alchemy that danced in secret chambers while Newton gave us gravity, while he wrote the Principia, while he became the Newton we remember even though the Newton we remember is incomplete. Is simplified is the public Newton while the private Newton danced with alchemy, sought transmutation, believed in mysteries, pursued the philosopher's stone, worked in secret chambers, the alchemy dancing, the seeking continuing, the Newton who was more than physics, more than mathematics, more than mechanism, more than we want him to be, the alchemy revealing, the secret chambers preserving, the dancing continuing in memory, in manuscripts, in the recognition that genius is complex. That Newton was both scientist and alchemist, both the laws and the stones, both the public achievement and the secret pursuit, both the Principia and the alchemy, both the Newton who rewrote the heavens and the Newton who sought to transmute matter, both dancing together in the complex man who was Newton, the alchemy that danced in secret chambers showing us truth. As Newton's mechanics explained more of nature's operations, as gravity and motion became mathematical laws, as the Principia demonstrated that the cosmos operates according to fixed principles, a question emerged that troubled Newton deeply: if the universe is machine running according to laws, where does God act? If everything follows necessarily from initial conditions and natural law, what role remains for divine providence? If the cosmos is clockwork mechanism, does it need the clockmaker only at the beginning, to wind it and set it going, or does God remain active, necessary, involved in ongoing governance of creation? Newton rejected the implication that his physics made God unnecessary, insisted that natural law revealed divine wisdom rather than replacing divine action, believed that understanding mechanism was understanding the mind of God, that mathematics expressed divine thought, that the laws he discovered were God's laws, that studying nature was studying God's works. The mechanical universe was not, for Newton, evidence against God, but was evidence for God, the elegance of natural law, the mathematical beauty of planetary motion, the precise adjustment of gravitational force that kept solar system stable. All these pointed toward designer of supreme intelligence, toward creator who had structured nature according to rational principles, toward God whose wisdom was displayed in the lawfulness of creation. But the metaphor of the clock created tensions that Newton recognized even while using it, problems that would grow larger as later generations took the mechanical universe more seriously than Newton himself did, that would lead to deism that saw God as distant watchmaker who wound the clock and departed, that would culminate in Laplace's response to Napoleon's question about God's role in the cosmos. I have no need of that hypothesis. Newton would have been horrified by this conclusion, would have rejected utterly the suggestion that physics made God unnecessary, would have insisted that natural law pointed toward lawgiver, that mechanism required intelligent designer, that the clockwork cosmos demonstrated rather than diminished divine wisdom. Yet Newton's own physics created space for the doubt he would have rejected, suggested that once laws were established and initial conditions set, the universe could run by itself without requiring ongoing divine intervention, that miracles became violations of natural law rather than being ordinary divine action, that providence became problematic if everything followed necessarily from mechanical causes, that God's role became unclear in universe governed completely by mathematics and matter in motion. The tension was real, was felt by Newton himself, shaped his theology in ways that his physics alone could not determine. Specifically, Newton believed God must occasionally intervene to maintain the solar system's stability, that planetary perturbations would eventually cause orbits to decay unless God periodically adjusted them, that the clockwork cosmos was not quite self-sustaining, required divine maintenance to keep running properly, that natural law described God's ordinary operations, but that God retained power to act extraordinarily when necessary. That the universe needed its creator not just at the beginning but continuously, for preservation and governance and occasional correction of irregularities that natural law alone could not prevent. Later physics would show Newton was wrong about orbital instability, would demonstrate that the solar system is more stable than he believed, would eliminate the need for divine intervention to maintain planetary orbits, would make the mechanical universe more completely self-sufficient than Newton had thought possible. But Newton's error was revealing, showed he wanted God to be necessary, needed the cosmos to require its creator, could not accept that natural law might be complete, that mechanism might be self-sustaining, that the clock might run forever without the clockmaker's ongoing involvement, that physics might explain everything within its domain without needing to invoke God except as original cause, as first mover, as the one who established laws and set initial conditions, but who might then withdraw, might leave creation to operate according to principles that required no further intervention. The theological stakes were enormous if the universe's self-sufficient mechanism, what prevents slide into atheism. If natural law is complete, what role remains for God? If everything happens according to mechanical necessity, where is freedom, where is providence, where is the moral order that requires God to reward virtue and punish vice? Newton saw these dangers, recognized that mechanical philosophy could undermine religious belief if pushed too far, if interpreted too mechanistically, if made into complete worldview rather than being limited to description of material interactions, to explanation of how things move without claiming to explain why they exist, why there is something rather than nothing, why the laws are what they are. In this space between mechanism and meaning, between physics and metaphysics, between explaining how nature operates and explaining why there is nature at all, Newton placed God not as hypothesis within physics, not as explanation of mechanical details, but as foundation for everything, as reason why there are laws, as ground of existence itself, as the necessary being on which contingent universe depends. As the intelligence that designed the clock, even if the clock then runs according to its own principles, as the creator without whom there would be nothing to be mechanical, no laws to govern, no cosmos to study, no physics to pursue. The silence where God wound the clock is the silence beyond mechanism, the recognition that even complete mechanical explanation leaves ultimate questions unanswered, that physics describes without creating, explains operations without accounting for existence, discovers laws without explaining why there are laws, that the success of natural science does not eliminate but rather deepens the mystery of why there is nature to be scientific about, why the universe submits to mathematical description, why comprehension is possible, why there is something rather than nothing, why this cosmos rather than some other or none at all. Newton lived in this silence, believed both that physics was complete in its domain and that its domain was limited, that mechanism was real but mechanism was not everything, that natural law governed material interactions but that natural law itself required explanation, required lawgiver, required God who was not hypothesis within physics but was foundation of physics, ground of the intelligibility that made physics possible, reason why nature submits to mathematics. Why the universe can be understood, why the clock works according to principles that Newton discovered but could not ultimately explain, could describe but could not derive from anything more fundamental, could express mathematically but could not say why mathematics applies, why nature is lawful, why the universe is cosmos rather than chaos. The clock wins, the mechanism operates, the laws govern, the planets orbit, the cosmos continues according to principles that Newton revealed. But the questions remain: why this clock? Why these laws? Why mechanism at all? Why something rather than nothing? The silence holds these questions, preserves them beyond physics' reach, maintains them as mysteries that natural science cannot address, that point toward metaphysics, toward theology, toward the ultimate ground that Newton called God, that he believed was necessary even though physics did not need to invoke God as explanatory principle, that he insisted was real even though mechanism was complete in its own domain, that he placed in the silence where the clock was wound, where the laws were established, where existence was created, where the cosmos began, where God acted in ways that physics could not capture but that Newton believed were real, were necessary, were the foundation without which there would be no clock to wind, no laws to discover, no cosmos to understand. The silence where God wound the clock, holding the mystery beyond mechanism, the question beyond physics, the ground beyond natural law, the necessity beyond contingency, the creator beyond creation. The God that Newton believed in even while giving us the mechanical universe, the silence preserving what mechanism cannot explain, what physics cannot address, what natural law cannot derive, the ultimate mystery that remains even after Newton's achievements, even after the Principia, even after the laws are discovered and the mechanisms are understood and the cosmos is explained. The silence where God wound the clock, where ultimate questions dwell, where Newton believed God acts. Where mechanism meets meaning, where physics meets metaphysics, where the comprehensible universe reveals its foundation in mystery, in the silence where God wound the clock. Newton's life divided like light through prisms: scientist and alchemist, mathematician and theologian, public genius and private mystic, the man who gave us natural law and the man who calculated biblical prophecy, president of the Royal Society who also wrote treatises on the Temple of Solomon, physicist who studied mystical texts, rationalist who believed in hidden wisdom, mechanist who practiced alchemy. The divisions were not failures of consistency, but were aspects of single quest for understanding, different approaches to comprehending nature and scripture, and the divine mind that created both, varied tools for pursuing truth that Newton believed was unified even though its investigation required multiple methods, diverse techniques, approaches that seemed contradictory to later generations, but that Newton experienced as complementary, as different paths toward the same destination. The historical Newton is harder to categorize than the legendary Newton, refuses to fit the image of pure scientific rationality that Enlightenment wanted to celebrate, remains complex where simplification is desired, mystical where pure reason is expected, heterodox where orthodoxy is preferred. The real Newton wrote more about theology than about physics, spent more time on alchemy than on the work that made him famous, devoted decades to biblical chronology and prophecy, believed the Temple of Solomon encoded divine wisdom, thought ancient texts preserved truths that modernity had lost, pursued the philosopher's stone alongside the laws of motion, sought transmutation while discovering gravitation. Later generations struggled with this multiplicity, wanted to preserve the Newton they could celebrate while ignoring the Newton who troubled their image of what genius should be, what the founder of modern science should have believed, what rationality should look like. They tried to separate the scientist from the alchemist, the physics from the theology, the principia from the prophetic studies, tried to extract the pure science from the impure mysticism, tried to make Newton fit categories he had not recognized, tried to simplify what was irreducibly complex. The effort failed because the real Newton will not cooperate with simplification, remains stubbornly multiple, insists through his manuscripts that he was all of these things, that genius cannot be reduced to its acceptable parts, that greatness includes what we would exclude. The prism that splits Newton's genius into spectrum reveals that the boundaries we draw between legitimate science and illegitimate pseudoscience, between rational inquiry and mystical speculation, between physics and metaphysics, were not so clear to Newton, were not barriers he respected, were not limits he accepted. For Newton, alchemy and physics were different approaches to understanding nature, both valid, both necessary, both revealing aspects of reality that the other could not fully capture. Theology and mathematics both disclosed divine wisdom, both gave access to truths about creation, both were worth pursuing with equal dedication. The ancient texts and modern experiments both contained knowledge worth having, both taught lessons worth learning, both contributed to the unified understanding that Newton sought. What looks like contradiction from outside may have been coherence from inside, may have been recognition that the universe is richer than any single approach can capture, that understanding requires multiple methods, that wisdom comes from diverse sources, that restricting inquiry to what later ages would call science means missing dimensions of reality that other approaches reveal. Newton's genius was not in choosing correctly between science and alchemy, but in pursuing both with equal rigor, not in separating physics from theology, but in seeing how they complement each other, not in being purely rational, but in recognizing that reason has limits, that mystery persists, that the universe contains more than mechanism, even though mechanism is real and powerful and illuminating. The spectrum into which Newton's genius divides shows all the colors: the physics that succeeded, the alchemy that failed, the theology that was heterodox, the mathematics that was revolutionary, the mysticism that was sincere, the biblical chronology that was serious scholarship even though wrong, the prophetic interpretation that was deeply believed even though misguided. All of these were expressions of the same mind, the same quest, the same devotion to understanding that manifested differently in different domains, but that was fundamentally unified in seeking truth, in pursuing wisdom, in attempting to comprehend the cosmos that God had created and the scriptures that God had inspired and the natural laws that God had established. We inherit layered Newton, the legend who embodies Enlightenment rationality, the historical figure who was stranger and more complex, the genius who gave us classical mechanics but who also sought the philosopher's stone, the founder of mathematical physics who also believed in ancient wisdom, the man who rewrote the heavens but who also calculated the apocalypse. We can choose which Newton to celebrate, which to ignore, which to emphasize in telling his story. But the complete Newton includes all of these, refuses to be reduced to comfortable legend, insists on being understood in full complexity, demands that we accept the spectrum rather than extracting single color, that we acknowledge the multiplicity rather than imposing false unity. The prism teaches that genius is rarely what we want it to be, that minds that change our understanding are often stranger than we prefer, more contradictory than we can comfortably accept, more complex than our categories can accommodate. Newton the scientist cannot be separated from Newton the alchemist without losing something essential, without simplifying beyond recognition, without creating fiction rather than preserving history. The man who gave us the mechanical universe also believed the universe was more than mechanism, also pursued mysteries that mechanism could not explain, also honored ancient wisdom that rationality might dismiss, also remained open to dimensions of reality that pure science could not capture. Perhaps this is the lesson that genius includes what we would exclude, embraces what we would reject, pursues what we would dismiss, that the boundaries between acceptable and unacceptable inquiry are more permeable than we assume, that wisdom comes from unexpected sources, that understanding is multiple rather than singular, that the spectrum is richer than any single color. That Newton was all of these and was greater for being all of them rather than being diminished by the parts that don't fit our preferred image. The prism splits genius into spectrum, reveals the complexity, shows the multiplicity, makes visible what simplification conceals, what legend obscures, what celebration of pure rationality misses the strange, mystical, alchemical, theological Newton, who was as real as the mathematical, physical, mechanical Newton, who deserves to be known alongside the celebrated physicist, who completes rather than contradicting the genius we honor. The spectrum shows us Newton whole scientist and alchemist, physicist and theologian, mathematician and mystic, the man who gave us laws and sought stones, who explained motion and pursued transmutation, who was both and was neither, who was the complexity that the prism reveals when we look carefully rather than simplifying, when we accept multiplicity rather than demanding purity, when we let genius be what it was rather than making it what we want. The prism splitting Newton into spectrum that includes physics and alchemy and theology and prophecy and mathematics and mysticism all together, all part of the same pursuit, all expressions of genius that cannot be reduced, cannot be simplified, cannot be made to fit our categories. The prism revealing the truth that genius is spectrum, that understanding is multiple, that Newton was all of these, was the spectrum that we inherit when we look beyond the legend to the historical figure. Beyond the celebration to the complexity, beyond the convenient fiction to the difficult truth, the prism splitting genius into spectrum, showing us Newton complete. In 1693, in the midst of his powers and prominence, something broke in Newton, a crisis, a breakdown, a period of months when the mind that had given us gravity and calculus and optics fractured. The letters he wrote were strange, paranoid, accusatory, suggesting friends had betrayed him, that he could no longer trust, could no longer think clearly. To John Locke, accusations of trying to embroil him with women. To Samuel Pepys, claims that life had become unbearable, that death would be preferable. The communications worried those who received them, suggested Newton's mind was compromised, that the clarity and precision that characterized his work had given way to confusion and distress and something approaching madness. What caused the breakdown remains mysterious even after 3 centuries of speculation. Was it mercury poisoning from decades of alchemical experiments, the toxic accumulation finally reaching levels that affected cognition and mood? Was it exhaustion from maintaining genius at highest pitch for too long, the strain of pursuing too many investigations simultaneously, of trying to understand too much too deeply? Was it disappointment, romantic, professional, intellectual, that Newton never discussed but that ate away at him until the strain became unbearable? Was it theological crisis, recognition that his beliefs were heretical, that he could never publish his true views without risking everything, the burden of permanent deception finally proving too heavy? The evidence is fragmentary, the letters suggestive but not conclusive, the symptoms consistent with various diagnoses but not definitive for any, leaving us with mystery, with breakdown whose cause we cannot determine with certainty, with crisis that damaged the greatest mind of the age but whose origins remain elusive. Newton recovered within months. He was functioning again, was productive again, went on to accomplish more, to reform the currency, to serve as president of the Royal Society, to revise the Principia, to continue his theological studies. But those who knew him said he was never quite the same, that something had changed, that the fever had left marks, that genius had been touched by something it could not fully recover from. The breakdown reveals genius's vulnerability, shows that even Newton's mind had limits, that the intensity required to achieve what he achieved came with costs, that understanding too much or too deeply or for too long might be dangerous, that the mind that knew too much about nature and scripture and alchemy and mathematics might know more than human cognition can sustain, might exceed safe boundaries, might push beyond limits that exist for reasons that protect us from knowing more than we can bear. Perhaps there are things humans are not meant to understand completely, depths we should not explore fully, knowledge that comes at price too high, understanding that damages those who achieve it. The fever suggests that genius is fragile, that brilliance has breaking points, that the mind capable of revolutionizing physics is also capable of cracking under strain that ordinary minds would never experience because ordinary minds never reach the heights where the pressure becomes unbearable. Newton climbed higher than anyone had climbed before, saw farther than anyone had seen, understood more deeply than anyone had understood, and the altitude brought not just triumph but also danger, not just revelation but also risk, not just achievement but also the possibility of falling, of breaking, of the fever that comes from being too high, knowing too much, understanding too deeply. The mystery of what broke Newton, of what caused the fever that cracked the mind that knew too much, may be unanswerable. The evidence is insufficient, the distance is too great, the inner life of genius too private to be reconstructed with certainty. But the fact of the breakdown is undeniable, is recorded in letters that survive, is reported by friends who witnessed it, is real event in Newton's life even if its cause remains unclear. And the fact teaches something important, that genius is human, that minds can break regardless of how brilliant they are, that achievement comes with cost, that knowing too much has dangers, that the fever is real and the crack is real, and even Newton was vulnerable. We close in the silence after fever, in the recognition that Newton survived but was changed, that genius continued but bore scars, that the mind recovered but remembered the breaking. The year 1693 remains mysterious, remains the moment when something gave way, when the strain proved too much, when the mind that knew too much learned its limits through breaking, through fever, through the crisis that history records but cannot fully explain, that we can witness but cannot fully understand, that reveals genius's fragility, brilliance's vulnerability, the price of being Newton, of achieving what he achieved, of knowing what he knew, of pursuing understanding with intensity that brought both triumph and danger, both revelation and risk, both the achievements we celebrate and the fever we remember, the breakdown that showed genius is human, that minds have limits, that even Newton could not escape the vulnerabilities that all minds share, that the fever was real, that the crack was real, that knowing too much comes with cost, that the mind that knew too much learned this through breaking, through the crisis of 1693. Through the fever that cracked the mind that knew too much. In Westminster Abbey, among kings and poets and those deemed worthy of the nation's highest honor, Newton was buried with ceremony that no scientist before him had received. The monument shows him reclining, surrounded by symbols of his achievements, prisms and telescopes, planetary orbits and mathematical instruments, the tools and tokens of genius who gave us the mechanical universe. The Latin inscription proclaims that mortals should rejoice that such glory to the human race existed, turning Newton into more than individual, into representative of human possibility, into proof that we are capable of understanding, that reason can reach truth, that the universe submits to inquiry. But the monument's shadow extended beyond celebration. Newton became burden as well as inspiration, became standard against which all subsequent science was measured and found wanting, became the genius so complete that he seemed to have said the last word, discovered the final laws, achieved the ultimate understanding. How could anyone follow Newton? What could be discovered that he had not already found? The anxiety of influence was overwhelming. The shadow cast by the monument seemed to darken all of science, seemed to suggest that everything important had been accomplished, that only refinement remained, that genius had exhausted its possibilities, that Newton had achieved what physics could achieve. For 2 centuries the shadow persisted. Newton's laws reigned supreme. Classical mechanics explained everything within its domain. The Principia stood as ultimate achievement. The monument in Westminster Abbey reminded each generation that genius had already spoken, that the mechanical universe had been explained, that physics was essentially complete. But then Einstein came, showed that Newton's laws were approximations, that gravity was not force but curvature of spacetime, that mechanics must be relativistic at high velocities, that the Newtonian universe was special case of more general theory, that genius had not said the final word but had said a word that would be superseded. The recognition that Newton could be surpassed was both humbling and hopeful. Humbling, because it showed that even the Principia was not ultimate truth, that even Newton's genius had limits, that laws that seemed eternal were actually contingent, were valid in certain domains but not universally. But hopeful because it showed that science continues, that understanding progresses, that what seems final is really provisional, that genius does not exhaust truth but opens it, that Newton's achievement did not end physics but began modern physics, created framework that would eventually need revision, but that was necessary stage in developing understanding. The infinite shadow teaches that genius is both destination and departure, both culmination and commencement, both the height that seems unsurpassable and the platform from which further ascent becomes possible. Newton was both end and beginning, both final word of classical physics and first word of physics that would eventually transcend classical limitations, both the monument that seems to complete and the shadow that extends forward into future where his laws would be refined, corrected, superseded, incorporated into larger frameworks that preserved what was right while extending beyond what Newton could have imagined. Standing in Westminster Abbey, looking at the monument, feeling the weight of history, we recognize that Newton's shadow is not darkness but is the continuation of light, is the extension of illumination forward through centuries, is the foundation on which later physics builds. Einstein stood on Newton's shoulders. As Newton said, he stood on the shoulders of giants, looking farther because of the height that previous achievement provides, seeing more because genius created the platform, understanding more deeply because brilliance made deeper understanding possible. The monument honors genuinely, the shadow extends truly. Newton's achievements were real and lasting even though they were not final. Genius deserves reverence even though reverence should not prevent surpassing. Monuments cast shadows, but shadows are not obstacles, are instead the shade from which new growth emerges, new understanding develops, new genius appears. The monument in Westminster Abbey makes possible the very surpassing it seems to prevent. The shadow enables the light that will come. Newton's infinite shadow casting forward through centuries, through relativity, through quantum mechanics, through all the physics that followed and that built on his foundations even while transcending his conclusions. The infinite shadow is not burden but is blessing, is not ending but is beginning, is not completion but is invitation, is not the final word but is the first word that makes later words possible, is not the achievement that prevents further achievement, but is the foundation that enables it, is not darkness, but is light extending, is not monument freezing understanding, but is monument making understanding possible to progress, to develop, to surpass even supreme achievement. To honor genius by continuing the work genius began, to reverence Newton by doing what Newton did, questioning, discovering, understanding, revealing nature's laws. The shadow is infinite, extending forever, encompassing all who came after, all who built on his achievements, all who honored him by surpassing him, all who stood in his shadow and reached toward light, continuing what Newton began, extending what Newton achieved, surpassing what Newton accomplished while remaining forever in the shadow of the monument, in the infinite shadow that Newton casts from Westminster Abbey, from the Principia, from the genius that gave us laws that shaped the universe, that explained the cosmos, that made physics possible, that created the understanding we inherit. We dwell in Newton's shadow still, build on his foundations, extend his insights, surpass his conclusions while honoring his achievements, stand on his shoulders while looking farther, use his mathematics while developing new mathematics, accept his methods while refining them, recognize his limits while celebrating his genius, knowing that the monument in Westminster Abbey honors the man who gave us the laws, who explained the cosmos, who showed that reason can comprehend nature, who demonstrated what genius can achieve, who cast the infinite shadow that we inherit, that we dwell in, that we continue building from, reaching toward new light while remaining forever in Newton's shadow, in the infinite shadow that the monument casts, that genius creates, that achievement makes possible, forever Newton, forever the laws, forever the shadow, infinite. Newton's laws became the grammar of classical physics, the language in which all motion was described, the framework within which all mechanical phenomena were understood. For 2 centuries, every physicist learned to think in Newtonian terms, to reduce problems to forces and masses and accelerations, to translate natural phenomena into equations that Newton's methods could solve. The liberation was real problems that had resisted all previous approaches yielded to Newtonian mechanics. Phenomena that seemed chaotic revealed themselves to be lawful. The universe that had seemed mysterious became comprehensible, calculable, predictable. But liberation gradually became imprisonment. The very success of Newton's laws made it difficult to imagine alternatives, to question whether mechanics might need revision, to recognize that classical physics had limits. The equations worked so well, explained so much, achieved such precision in their predictions that they seemed to be ultimate truth rather than useful approximation, seemed to capture reality itself rather than describing reality within limited domain. The framework became invisible, the assumptions became unquestionable, the limits became unrecognizable because everything within those limits worked perfectly, seemed complete, appeared final. The imprisonment was subtle, not external restriction, but internal limitation, not prohibition against questioning, but inability to see what should be questioned, not enforcement of orthodoxy, but comfort with framework that worked, that explained, that achieved such success that alternatives seemed unnecessary, that revision seemed impossible, that surpassing seemed unimaginable. Newtonian mechanics became not just dominant framework, but seemed to be the only possible framework, the necessary structure of any physics, the eternal truth about motion that could be refined but never fundamentally revised. But the universe resisted complete containment. Even in Newton's elegant cage phenomena emerged that classical mechanics struggled to explain, observations that suggested limits to Newtonian framework, hints that revision might be necessary even though revision seemed impossible. The orbit of Mercury precessed slightly more than Newton's laws predicted, a tiny discrepancy that classical mechanics could not quite explain. Light speed seemed constant regardless of observers' motion, a result that violated Newtonian assumptions about how velocities should add. Blackbody radiation followed patterns that classical physics could not derive, suggesting that something fundamental was missing, that the framework might be incomplete. The hints accumulated slowly, the discrepancies were small, the anomalies could be dismissed as mere puzzles that would eventually be solved within classical framework. But they persisted, resisted explanation, suggested that Newton's laws were not final truth, but were approximations valid within certain domain, but requiring revision when pushed to extremes: very high velocities approaching light speed, very strong gravitational fields, very small scales where quantum effects dominate, domains where classical physics breaks down, where new frameworks become necessary, where Einstein and quantum mechanics would eventually succeed by abandoning Newtonian assumptions. By questioning what seemed unquestionable, by recognizing that liberation had become imprisonment, that success had created blinders, that the equations that explained so much also prevented seeing beyond what they explained. The liberation was real, the imprisonment was real. Both were consequences of Newton's achievement, laws so successful that they dominated physics for 2 centuries, but also so successful that they made alternatives difficult to imagine, revision difficult to contemplate, surpassing difficult to achieve. Einstein's genius was partly in recognizing that Newton's laws were approximations, that classical mechanics worked wonderfully within its domain, but that its domain had limits, that different physics was necessary at high velocities and in strong gravitational fields, that space and time were more strange than Newton imagined, that gravity was not force but was geometry, that the universe was weirder and more wonderful than classical physics allowed. The equations that liberated also imprisoned, that explained also blinded, that achieved such success that they became obstacle to further progress, that worked so well that they prevented seeing what they could not explain, that created framework so comprehensive that escaping it required genius comparable to Newton's own, required Einstein willing to question what seemed unquestionable, to revise what seemed eternal. To recognize that even Newton's laws were not final truth, but were stages in understanding's progress, were steps toward deeper comprehension rather than being ultimate destination. We inherit both. The liberation and the imprisonment use Newton's laws daily because they work beautifully within their domain, solve innumerable problems with classical mechanics because its equations capture reality well enough for most purposes, benefit from the framework that Newton created. But we also know the limits, recognize the approximations, understand that classical physics is not complete, that relativity and quantum mechanics transcend Newtonian framework, that the universe is stranger than the mechanical clockwork that Newton described, that the equations liberate within their domain but would imprison if we believed they were complete, if we accepted them as final, if we forgot that even supreme achievement is provisional, that even Newton's laws can be surpassed. That liberation becomes imprisonment when we stop questioning, when we accept framework as eternal rather than recognizing it as stage in ongoing quest for understanding. The equations that liberated and imprisoned teach us that success is double-edged, that achievement creates both possibilities and limitations, that frameworks that explain also constrain, that progress requires recognizing when liberation has become imprisonment, when what worked must be transcended, when equations that served magnificently must be revised, when even Newton's laws must be seen as approximations rather than as final truth. When the liberation they provided must be acknowledged alongside the imprisonment they created, when we must honor Newton's genius while also recognizing its limits, when we must use his equations while also understanding their domain, when we must appreciate the liberation while also escaping the imprisonment, maintaining both reverence for achievement and willingness to surpass it, both gratitude for what Newton gave us and recognition that what he gave us, magnificent though it was not the final word, was not ultimate truth, was liberation that became imprisonment until Einstein freed us again, until relativity transcended classical mechanics, until the equations that liberated were recognized also to imprison, were understood to be approximations, were surpassed while still being honored, were both celebrated and transcended, were the liberation and the imprisonment both, the equations that shaped physics for 2 centuries but that also constrained it, that explained brilliantly but that also blinded, that were Newton's gift and Newton's burden both, the equations that liberated and imprisoned, that we still use and still surpass, that we still honor and still transcend. The equations that are Newton's legacy, both the achievement and the limitation, both the liberation and the imprisonment, both what we inherit and what we must move beyond, the equations that liberated and imprisoned. Chapter 11. The lonely nights when stars became mathematics, in the hours when darkness settled over Cambridge, when others slept and the city grew silent, Newton sat with stars, not observing them through telescopes, not merely noting their positions, but translating them into mathematics, transforming the celestial into the calculable, making the heavens submit to equations, turning the ancient mystery of planetary motion into problem that geometry could solve, that calculus could describe, that human reason could comprehend. The work was solitary, was labor of mind that could not be shared, required concentration that company would shatter, demanded the peculiar solitude that genius seems to need, the isolation that allows complete immersion in problems too complex for divided attention, too demanding for interrupted focus. The loneliness was chosen, but was also burden. Newton withdrew from society not because he disliked people, but because the work demanded it, because understanding planetary orbits required months of sustained calculation, because transforming stars into mathematics was a task that could not be accomplished in social hours, could not be pursued while maintaining ordinary relationships, could not be achieved without sacrifice, without the lonely nights when others slept and Newton calculated. When society celebrated and Newton worked, when companionship called and Newton remained alone with equations, alone with the heavens becoming mathematics, alone with the transformation that would change physics forever, but that required loneliness as its price. The stars resisted at first. Planetary motions were complex, involved epicycles and eccentricities that seemed arbitrary, that defied simple geometric description, that appeared to require ad hoc additions rather than following from fundamental principles. But Newton persisted, refused to accept that the heavens were ultimately mysterious, insisted that planetary orbits must follow from gravitational attraction and laws of motion, that ellipses were not arbitrary shapes but were necessary consequences of inverse square force, that Kepler's empirical laws could be derived from deeper principles, that the stars would yield to mathematics if mathematics was pursued with sufficient rigor, sufficient patience, sufficient willingness to sit alone night after night working through calculations that no one would appreciate, that no one would understand, that Newton himself might not complete, that might prove futile, that might lead nowhere, but that might unlock the heavens, might show how stars become mathematics, might demonstrate that celestial mechanics follows from same laws that govern earthly motion. The breakthrough came slowly, emerged gradually from months of calculation, revealed itself not as sudden flash but as dawning recognition that the mathematics worked, that gravitational attraction really did produce elliptical orbits, that Kepler's laws really did follow from Newton's principles, that the heavens really were comprehensible, really did submit to calculation, really were mathematical rather than ultimately mysterious. The triumph was private, was experienced alone in the lonely hours when Newton worked while others slept, when he calculated while others celebrated, when he transformed stars into mathematics through labor that no one witnessed, that no one appreciated at the time, that seemed merely eccentric isolation rather than the work that would revolutionize astronomy, that would make celestial mechanics into science, that would show the heavens obey same laws as earth. But loneliness had costs. Newton's isolation became habit, became inability to connect even when connection was desired, became withdrawal that protected the work but that also prevented relationships, that preserved focus but that also created distance, that made genius possible but that also made friendship difficult, that allowed the concentrated attention necessary for transforming stars into mathematics, but that also prevented the human warmth that makes life bearable. That gives meaning to achievement, that makes success worth having. Newton's greatness was inseparable from his loneliness. His achievements were made possible by his isolation. his transformation of the heavens was accomplished during lonely nights that were both necessary for the work and damaging to the man. We sit in those lonely hours now, centuries later, benefiting from the work that was accomplished in isolation, using the celestial mechanics that Newton developed alone, calculating planetary positions with equations that emerged from lonely nights when stars became mathematics. We honor the achievement, celebrate the genius, recognize the transformation that Newton accomplished. But we also acknowledge the cost, recognize the loneliness, understand that genius came with sacrifice, that the work required isolation, that transforming stars into mathematics demanded lonely nights, required choosing work over companionship, equations over relationships, understanding over connection, the heavens over human warmth. The lonely nights when stars became mathematics stand as monument both to what genius can achieve and to what genius must sacrifice, both to the transformation that Newton accomplished and to the isolation that transformation required, both to the success that we celebrate and to the loneliness that made success possible, both to achievement that changed astronomy forever and to the human cost of that achievement, to the lonely nights that produced the Principia but that also shaped the man. That made genius possible, but that also prevented happiness, that gave us celestial mechanics, but that also created the isolation, the withdrawal, the loneliness that characterized Newton's life, that enabled his work, that made the transformation possible, that allowed stars to become mathematics during lonely nights when Newton sat alone, calculating while others slept, working while others celebrated, transforming the heavens while sacrificing human connection. The lonely nights when stars became mathematics, when genius worked in isolation, when achievement came at cost of loneliness, when the transformation required the sacrifice, when stars became mathematics through lonely nights that we remember, that we honor, that we recognize as both triumph and tragedy, both achievement and sacrifice, both what genius accomplished and what genius lost, the lonely nights when stars became mathematics. Chapter 12, The Infinite Descent into Light and Shadow. At the end, we recognize that Newton was both light and shadow, achievement and mystery, the man who explained the cosmos and the man who could not explain himself, the genius who gave us laws and the human who broke under strain, the physicist who mechanized nature and the alchemist who sought living transformation, the rationalist who mathematized motion and the mystic who believed in ancient wisdom. The paradoxes cannot be resolved, should not be simplified, must be held together if we are to understand Newton complete rather than Newton reduced to comfortable legend, Newton made safe by selecting only what fits our image of Enlightenment rationality. The descent into Newton's world reveals layers: the public achievement beneath which lies private struggle, the celebrated laws beneath which lies lonely labor, the mechanical universe beneath which lies mystical cosmology, the rationality beneath which lies heterodoxy, the clarity beneath which lies complexity. Each layer reveals more, makes Newton stranger, makes genius more mysterious, makes achievement less straightforward than celebration suggests. We descend through Newton, discovering not simplicity but multiplicity, not single narrative but braided stories, not coherent legend but contradictory reality, not the Newton we expect but the Newton who was both light and shadow, both clarity and mystery, both the man we can comprehend and the man who eludes comprehension. The infinite descent continues. There is always more to discover about Newton, more manuscripts revealing new dimensions, more complexity emerging from closer study, more mystery appearing beneath apparent clarity. The historical Newton is inexhaustible, refuses to be completely known, preserves secrets despite centuries of scholarly investigation, remains partially mysterious despite being most studied scientist in history. The descent is infinite not because Newton deliberately concealed himself, but because genius is complex, because achievement is multifaceted, because the man who transformed physics was also transformed by physics, was shaped by his work while shaping our understanding, was changed by his achievements while changing astronomy, was both the agent of transformation and the subject transformed. The light Newton brought was real. The laws he discovered still govern classical physics. The mathematics he created still describes motion. The framework he established still structures mechanical understanding. But the shadow was also real. The loneliness, the breakdown, the heterodoxy, the alchemy that failed, the theology that remained private, the complexity that legend obscures, the mystery that genius preserves. The infinite descent into light and shadow reveals both, honors both, acknowledges that Newton was both and that both matter, that we cannot celebrate only the light without acknowledging the shadow, cannot simplify genius into legend without losing what makes genius real, cannot reduce Newton to comfortable icon without betraying the historical figure who was stranger, more complex, more human than icon can be. We close not with resolution, but with recognition that Newton remains mysterious despite being explained, that genius resists complete comprehension even when its achievements are understood, that the infinite descent continues, that light and shadow both persist, that Newton was both and will remain both, that the man who gave us laws that shaped the universe also shaped the mystery of genius itself, also demonstrated that achievement comes with cost, also showed that understanding produces new mysteries. Also revealed that the infinite descent into light and shadow is journey without end, exploration without completion, recognition that deepens without resolving, acknowledgement that honors while accepting limits, that celebrates while recognizing complexity, that sees Newton whole both light and shadow, both achievement and mystery, both the genius who transformed physics and the man who could not be reduced to physics, both the laws and the loneliness, both the principia and the alchemy. Both the public achievement and the private struggle, both what we can explain and what remains mysterious, both Newton the legend and Newton the reality, both descending infinitely into light and shadow, both remaining after centuries of study, both persisting despite attempts to simplify, both real and both necessary for understanding Newton complete, for honoring genius that was both light and shadow, for recognizing that the infinite descent continues, that Newton remains mysterious. That genius resists final comprehension, that the man who gave us the laws that shaped the universe also gave us the example of genius that includes light and shadow both, achievement and cost both, clarity and mystery both, the infinite descent continuing, the exploration deepening, the understanding increasing while mystery persists, light and shadow both, forever Newton, forever descending, forever both, infinite. End.